Hi everyone, this is Dr. GVR Seshgiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and material subject. In this subject already we have discussed about various topics like simple stresses and strains, and then the simple shear force and bending moment diagrams, and theory of simple pure bending. And also we have seen last previous session, we have discussed about problem solving of some topics like simple bending and shear force and bending moment diagrams, and the slope and deflections of various beams. Now in this session I want to discuss about problem solving on thin cylinders and columns. So already we have discussed about thin cylinders and columns. What do you mean by thin cylinders and columns? Now in this session, so how to solve the problems? So whenever a given problem related to these thin cylinders and columns, how to apply the empirical relations and derived equations. So first of all, you should know about outcome. So students should be able to demonstrate the stresses induced in thin cylinders and derivation of formula for longitudinal and circumferential stresses, columns and struts. So in this, so stresses, what are the stresses induced in cylinders? First you have to see, and then derivation of formula for longitudinal and circumferential stresses and columns and struts. So in this, after completion of this module, the student can he should be able to answer the stresses and stresses induced in the cylinders and this longitudinal and circumferential stresses of columns. He can able to do the problems. So first one, problem one, so related to these thin cylinders, problem solving on thin cylinders. A steam boiler of 800 mm diameter is made up of 10 mm thick plates. So if the boiler is subjected to an internal pressure of 2.5 megapascal, so find the circumferential and longitudinal stresses induced in the boiler plates. Steam boiler, 800 mm diameter. The internal diameter is given 800 mm and is made up of 10 mm thick. The thickness of the boiler is 10 mm. If the boiler is subject to an internal pressure, so whenever this subjected to this boiler some internal pressure 2.5 megapascal, so then find the circumferential and longitudinal stresses induced in the boiler plates. So first of all, you should write the given data. So so the given data is the diameter of the boiler is 800 mm, the thickness of the boiler is 10 mm, and then internal pressure 2.5 megapascal converted into Newton per mm square. Already you know 1 megapascal is equal to 1 Newton per mm square. See, now solution we will see the circumferential stress induced in the boiler plates. So whatever you have discussed in the theory part, so those relation here apply. The sigma c, that is PD by 2T. So the circumferential stress induced in the boiler plate is 2.5 multiplied with the diameter is 800 by 2 into 10. So 100 Newton per mm square. It's converted into 100 megapascal. So already given the internal pressure 2.5 and diameter also you know given in the problem 800, and only substitution, formula substitution here. The thickness of the shell also given. So the circumferential stress or whoop stress is equal to PD by 2T for thin cylinders. So the longitudinal stress induced in the boiler plates. So the longitudinal plate is stress is PD by 4T. So the P is internal pressure 2.5, and then diameter is 800 by 4 into thickness of the boiler shell is 10. So longitudinal stress also have calculated. So that is 50 megapascal. So this first problem based on formulas only. You have to substitute the values given formulas. So how to calculate the circumferential stress and then longitudinal stress we have discussed. Now the problem 2, a thin cylindrical shell, thin drum. So cylindrical thin drum, 800 diameter and 4 meters long, is made of 10 thick plates. So if the drum is subjected to internal pressure of 2.5 megapascal. So determine its changes in diameter and length. Take E as 200 gigapascal and Poisson ratio is 0.25. So first of all, given data, write down. The given data is the diameter of the drum, that is 800 mm. The length of the drum, 4 meters. So converted into mm, so 4 into 10 cube. Clear? The thickness of the plate is 10 mm. The internal pressure, 2.5 Newton per mm square. So the modulus of elasticity, E, gigapascal. So converted into Newton per mm square. 200 multiplied with 10 to the power 9 Pascal. Pascal converted into Newton per meter square, converted into mm by 10 to the power 6 Newton per mm square. So you will get 200 into 10 cube Newton per mm square. The Poisson's ratio given 1 by m, that you can write in terms of mu also, 0.25. Now calculate change in diameter. We know that the change in diameter delta D is equal to PD square by 2T into E into 1 minus 1 by 2M. So here P value already you know, 2.5, D also given, thickness also you know, so only available values substitute in this formula. So 1 by 2 into 1 by m, so this is 1 by m, that is Poisson ratio given. So substitute in this, you will get 0.35 mm. The change in diameter you got. The change in length. So what is asked in this problem? Determine its changes in diameter and length whenever this drum is subjected to internal pressure. Change in diameter is completed, similarly change in length. So you also know that the change in length delta L is equal to PDL by 2T into 1 by 2 into 1 minus m. So already we have seen in a theory session. Now substitute those values here, 2.5 diameter and L and T and E. So all values substitute, you will get delta L. So problem 3, in the previous first problem, direct problem, formula substitution. And then the second one is, he has asked indirectly the changes in diameter and changes in length. And third problem, a cylindrical vessel, 2 meters long and 500 mm diameter. So length given and diameter also given. And thickness also given. The thickness of plate is 10 mm, is subjected to an internal pressure of 3 megapascal. So calculate the change in volume of the vessel. So take E is equal to 200 gigapascal and Poisson's ratio is 0.3. For the vessel material, the Poisson ratio is 0.3. So the given data, write down the given data, length of the vessel 2 meters, Diameter of vessel 500 meter. Thickness of the plate 10 mm. The internal pressure. Thickness of the plates and internal pressure 3 megapascal. And modulus of elasticity E 200 gigapascal. And Poisson's ratio 0.3. So so already you converted this megapascal into Newton per mm square. This one also convert into 200 into 10 cube Newton per mm square. So now substitute the formulas. So what he has asked here, calculate the change in volume of the vessel. So circumferential strain and then longitudinal. And then volumetric volume find out. So PD by 2TE into 1 minus 1 by 2M. Substitute P, T and T value already you know, and then E value also convert 200 into 10 cube Newton per mm square. So you will get sigma C, epsilon C and epsilon L. And then the volume 5 by 4 d square into L. So already we have calculated this, applied this PD by 2T into 1 minus 1 by 2M. PDL by 2T into 1 minus, this change in length and change in diameter. Similarly here circumferential. So what is the dimension changed here? Circumferentially and length and volume. Now apply the change in volume. Delta V. V is equal to V into epsilon C plus 2 epsilon L. So we will get 185 into 10 cube. Now problem 4. The columns and studs. Up to now we have seen thin cylinders. Now the columns and studs, how to solve the problems. A hollow alloy tube 4 meters long with external and internal diameters of 40 mm and 25 mm. The 4 meters long tube given and external internal diameters of 40 mm and 25 mm. The external diameter 40 mm and internal diameter 25 mm respectively was found to extend 4.8 mm under a tensile load of 60 kilonewtons. So find the buckling load for the tube with both ends spinning. So also find the safe load on the tube taking a factor of safety as 5. So factor of safety also given 5 and find the buckling load. So the given data L 4 meters. The external diameter of the column 40 mm. The internal diameter of the column 25 mm. And deflection delta L and tensile load 60 kilonewtons converted into newtons and factor of safety also given. So now the area of the tube calculate. So the area of the tube is 5 by 4 into d square minus d square. Why? Because here this internal, external and internal diameters are given. So hollow tube. The given condition is hollow tube. Hollow alloy tube. So that's why here take an area d square minus d square into 5 by 4. So substitute the given external and internal diameters and calculate area. Moment of inertia of the tube is 5 by 4 into d square minus small d to the power of 4. So we will get value 106 and 500 mm to the power of 4. So the strain in the alloy tube calculate using delta L by L relation and the modulus of velocity for the alloy load per area into strain. So strain sigma is equal to delta L is equal to PL by AE. So delta L by L is the strain. You can write P by AE. So this E is equal to, you can write this equation load per area into strain. So next, since the column is pinned as its both ends, therefore equivalent length of the column. So already you have studied in theory. The equivalent length of the column whenever the column is pinned at both ends. So L E is equal to L. So 4 into 10 to the 10 cube. Euler's buckling load. The buckling load is equal to pi square E I by L E square. Clear? So next, safe load for the tube. Buckling load for upon factor of safety. So you will get safe load for the tube. The problem 5, an I section just 400 mm by 200 mm by 20 mm. These are the dimensions given. And 6 meters long is used as a strut. This problem related to strut. So already you know what do you mean by column and what do you mean by strut. Already I have explained in the theory portion. Whenever the strut is both ends fixed, the condition given. So what is the Euler's crippling load for the column, and take Young's modulus for the just as 200 gigapascal. So converted into Newton per mm square. See the I section here shown 200 width. These two are flanges and this is web. So the depth is 400 and the dimensions are given. The x-axis y thickness is 20 and width is 200. So I-axis is equal to pi by 4 into d. So already given the BD by 12. So I-axis for rectangular section is, this is one section and another section, 1, 2 and 3 section. So the high symmetry section, this one. So that the moment of inertia about x-axis, so you can use this BD by 12. So this is BD by 12 minus 180 into 360 cube. So 20 and 20, 40, 400 minus 40. So you will get 360, this dimension. And 180 width. So substitute, we will get I. Similarly, IYY. Since IYY is less than the IXX, 2.91 you got. So therefore, the joist will tend to buckle in YY direction. So whenever this value is less than the IXX, so the failure occurs tend to the reference to the YY axis. So we shall take the value of IYY. So the column is fixed as its both ends. Therefore, equivalent length of the column, both ends fixed, LE is equal to L by 2. So what is the L? L already given in the problem. 6 meters converted into mm. So now apply Euler's crippling load for the column. Pi square E I by LE square. Pi square into E into I by LE. So you got Euler's crippling load. Pi square E by LE square, already we have derived this equation. So next one problem based on related to this columns hand conditions. So already you know the columns the hand conditions are both the ends are hinged. One end of the strut is fixed, other end is free. Both the ends are fixed. One end of the strut is fixed, other end is hinged, like that. So a solid round bar 3 meters long and 5 centimeters in diameter is used as a strut with both ends hinged. So take E is equal to 2 into 10 to the power of 5 Newton per mm square. So determine the crippling load when the given strut is used with the following conditions. So both the ends are hinged. One end of the strut is fixed, other end is free. Both the ends are fixed. One end of the strut is fixed and other end is hinged. So like this, conditions given. So according to these conditions, you have to solve the problem. A solid round bar, 3 meters long, the L given, the diameter given, and condition also given. Okay, one by one now we will see. So the length is 3 meters, and the external diameter of the column is 5 centimeter, and E is 2 into 24 5 Newton per mm square. So both the ends are hinged. So when the condition, the both ends are hinged, pi square EI by L square. So substitute the given values. So you will get value 67.288 kilonewton. So like this second one. Second condition, one end of the strut is fixed and other end is free. So what is the condition? Pi square EI by, first one is both ends hinged, pi square EI by L square. For this problem, P is equal to pi square EI by 4L square. So length and external diameter, and E. Now calculate, simplify this equation and you will get final answer. Similarly, third condition, both the ends are fixed. So that is P is equal to 4 pi square EI by L square. In previous one, pi square EI by 4L square. So see the difference. The both ends are fixed. So the formula is 4 pi square EI by L square. Substitute E value and I value and L value. Same as in the previous condition, you will get both ends are fixed load, crippling load.
Like, share and subscribe. Hit the bell icon for more updates.